In the depths of a physics laboratory, a single photon races toward two narrow slits cut into a barrier. This particle of light, smaller than anything you can imagine, is about to challenge everything you think you know about reality itself. When no one is watching, the photon behaves like a wave, passing through both slits simultaneously and creating an interference pattern on the screen behind. But the moment someone tries to observe which slit it goes through, something impossible happens. The photon suddenly chooses one path, abandoning its wave-like behavior entirely, as if it knows it's being watched. This isn't science fiction. This is the observer effect, one of the most profound mysteries in modern physics. And it suggests something that should terrify and fascinate you in equal measure. Reality might not exist until someone observes it. Before we dive into the quantum rabbit hole that will forever change how you see the world, hit that like button and subscribe, because what you're about to discover challenges the very foundation of existence itself. Prepare yourselves. We begin. Picture yourself walking through your house right now. The walls are solid, the floor supports your weight, and the furniture occupies definite positions in space. Everything seems real, permanent, and independent of your presence. But what if I told you that according to our best scientific understanding, none of these objects possess definite properties until the moment you observe them? What if the act of looking at something literally brings it into existence? This is the heart of the observer effect in quantum mechanics, a phenomenon so strange that even Einstein called it spooky. For over a century, physicists have struggled to understand what it means that observation appears to create reality. Some dismiss it as a measurement problem. Others embrace it as proof that consciousness shapes the universe, and a few suggest it reveals that we live in a participatory cosmos where reality emerges from the questions we choose to ask. The story begins in 1801 when Thomas Young conducted what seemed like a simple experiment to settle a debate about the nature of light. Scientists had argued for centuries about whether light consisted of particles, as Newton believed, or waves, as others proposed. Young's double-slit experiment was designed to provide definitive proof that light behaved as a wave, ending the controversy once and for all. The setup was elegant in its simplicity. Young shone light through two narrow slits cut into a barrier and observed the pattern that emerged on the screen behind. If light consisted of particles, you would expect to see two bright strips corresponding to the paths through each slit. Instead, Young observed something remarkable, an interference pattern of alternating bright and dark bands that could only result from waves passing through both slits simultaneously. The peaks and troughs of these waves interfered with each other, sometimes adding together to create brightness and sometimes cancelling out to produce darkness. Young's experiment seemed to settle the matter decisively. Light was a wave phenomenon, and Newton's particle theory was relegated to historical curiosity. The interference pattern provided clear evidence that light waves travelled through both slits at once, creating the characteristic zebra stripe pattern that became the signature of wave behaviour. But the emergence of quantum mechanics in the early 20th century transformed Young's elegant demonstration into something far more mysterious. Scientists discovered that light could be detected as individual particles called photons, each carrying a discrete packet of energy. This created a paradox that would haunt physics for generations. How could something be both a wave and a particle? The mystery deepened when researchers began shooting single photons through the double-slit apparatus one at a time. Logic suggested that individual particles should behave like tiny bullets, passing through either one slit or the other and creating two distinct impact zones on the detector screen. After all, a single particle cannot be in two places simultaneously, can it? What happened defied all common sense. Even when photons were fired individually, with long gaps between each emission, the interference pattern still emerged. Each photon somehow passed through both slits simultaneously, interfering with itself to create the wave-like pattern. It was as if each particle knew about the presence of both openings and adjusted its behavior accordingly. This phenomenon revealed something profound about the quantum world. Individual particles existed in what physicists call superposition states, occupying multiple possibilities simultaneously until something forced them to choose a definite outcome. The photon wasn't traveling through the left slit or the right slit. It was traveling through both until the moment it hit the detector screen and registered a specific location. But the story takes an even stranger turn when we introduce the observer. Curious about which path each photon actually took, scientists installed detectors at each slit to monitor the particle's behavior. These detectors could register when a photon passed through without significantly disturbing its energy or trajectory. The goal was simply to gain information about which slit each particle chose. The results shocked the physics community. The moment the detectors were activated to observe which slit each photon passed through, the interference pattern vanished completely. Instead of the wave-like zebra stripes, the screen showed exactly what you would expect from particles, two bright regions corresponding to the paths through each slit. The photons had abandoned their wave-like behavior and started acting like classical particles. Even more bizarrely, turning the detectors off restored the interference pattern. The photons seemed to know whether they were being observed and adjusted their behavior accordingly. When unobserved, they acted like waves passing through both slits simultaneously. When observed, they behaved like particles taking definite paths through individual slits. This wasn't simply a matter of the detectors physically disturbing the photons. Modern experiments have demonstrated the observer effect using detection methods so gentle they barely interact with the particles at all. The mere presence of which path information, regardless of whether anyone actually looks at the detector readings, is sufficient to destroy the wave-like behavior. The observer effect revealed something unprecedented about the nature of measurement in quantum mechanics. Unlike classical physics, where observation simply reveals pre-existing properties, quantum measurement appears to participate in creating the very reality it observes. Before measurement, quantum systems exist in superposition states containing multiple contradictory possibilities. The act of observation somehow selects one possibility from this quantum menu and makes it real. But what exactly constitutes an observation? This question has spawned decades of debate and multiple interpretations of quantum mechanics. The most widely accepted Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, treats observation as any interaction capable of extracting information from a quantum system. From this perspective, consciousness plays no special role. A detector, a computer, or even an environmental interaction can serve as an observer. Werner Heisenberg emphasized that the observer need not be conscious, writing that the transition from the possible to the actual is absolutely necessary and cannot be omitted. But it doesn't matter whether the observer is an apparatus or a human being. What matters is the registration of information, the irreversible recording of which possibility becomes reality. This interpretation suggests that the observer effect results from the fundamental difference between quantum and classical physics rather than any mystical connection between consciousness and reality. Quantum systems naturally exist in superposition states, but interactions with classical measuring devices force them to exhibit definite properties. The boundary between quantum and classical behavior, known as the Heisenberg cut, can be placed anywhere in the measurement chain as long as it includes the final recording device. However, not all physicists accept this mechanistic view of observation. Eugene Wigner, one of the pioneers of quantum mechanics, proposed that consciousness itself triggers the collapse of quantum superposition states. In his famous thought experiment known as Wagner's friend, he explored what happens when a conscious observer watches another conscious observer perform a quantum measurement. Wagner argued that the measurement chain must terminate somewhere, and that somewhere is consciousness. Physical instruments can become entangled with quantum systems, creating larger superposition states that encompass both the original system and the measuring device. Only conscious observation, he suggested, possesses the special property needed to collapse these superposition states into definite realities. This consciousness-based interpretation implies that mind plays a fundamental role in physical reality. Before consciousness evolved in the universe, Wigner's view suggests that quantum systems remained in superposition indefinitely, with no mechanism available to select definite outcomes from the quantum possibilities. The emergence of conscious observers would represent a phased transition in the nature of reality itself, transforming a universe of pure potential into one of actualized experience. Most physicists today reject Wigner's consciousness interpretation primarily because it seems to violate the principle that physics should not depend on subjective mental states. Science strives for objective descriptions of reality that don't depend on the presence or absence of conscious beings. Additionally, Wigner himself later abandoned this interpretation, recognizing the conceptual difficulties it created. Modern experiments have demonstrated that the observer effect occurs even when conscious beings are completely absent from the measurement process. Automated detection systems, environmental interactions, and purely physical processes can all destroy quantum superposition states without any conscious intervention. The quantum world appears to respond to information extraction rather than awareness. Yet the consciousness interpretation refuses to disappear entirely. Some physicists and philosophers continue to argue that consciousness might play a more subtle role in quantum mechanics than the Copenhagen interpretation acknowledges. They point out that our entire understanding of quantum mechanics comes from conscious observations of experimental results. We never directly experience quantum superposition states ourselves, only their classical consequences as recorded by measuring instruments. The debate over consciousness and observation connects to deeper questions about the nature of reality itself. If physical systems exist in superposition states until observed, what does this mean for the objective reality that science seeks to describe? Are we discovering a pre-existing universe, or are we participating in its creation through the act of investigation? John Wheeler, one of the most influential physicists of the 20th century, embraced the participatory view of reality. He coined the phrase, "it from bit," to express his conviction that information, rather than matter or energy, forms the fundamental substrate of reality. In Wheeler's vision, the universe emerges from the questions we choose to ask rather than existing as an independent entity waiting to be discovered. Wheeler's participatory universe suggests that observers don't simply reveal reality, they help create it through their choices about what to measure and how to measure it. Each observation represents a yes or no question posed to nature, and the accumulation of these binary choices constructs the classical reality we experience. From this perspective, the observer effect isn't a strange quirk of quantum mechanics, but the fundamental mechanism by which reality crystallizes from pure possibility. The delayed choice quantum eraser experiment, inspired by Wheeler's ideas, pushes the observer effect to its logical extreme. In this sophisticated version of the double-slit experiment, the decision to observe which path each photon takes can be made after the photon has already passed through the slits but before it hits the final detector screen. Remarkably, this delayed choice appears to retroactively determine whether the photon exhibited wave or particle behavior during its earlier journey through the apparatus. These experiments seem to suggest that future observations can influence past events, challenging our normal understanding of causality and temporal sequence. If observation truly creates reality rather than merely revealing it, then the timeline of creation might not follow the linear progression we expect. The choice to observe or not observe could reach backward in time to determine what actually happened in the past. However, most physicists interpret delayed choice experiments in terms of correlation rather than causation. The apparent retrocausal effects result from quantum entanglement between different parts of the experimental setup rather than actual backward time travel. The correlations exist timelessly in the quantum description, becoming manifest only when we make measurements that reveal the relationships between different events. Regardless of the specific interpretation, these experiments demonstrate that the observer effect operates in ways that violate our classical intuitions about the relationship between cause and effect. The act of observation appears to have consequences that extend beyond the immediate moment of measurement, influencing the entire causal structure of quantum events. The technological implications of the observer effect extend far beyond philosophical speculation into practical applications that are reshaping our understanding of information processing and computation. Quantum computers rely on maintaining quantum superposition states while carefully controlling when and how observations are made. The challenge lies in preserving the delicate quantum properties needed for computation while still allowing controlled measurements to extract useful information from the system. Engineers working on quantum technologies must treat the observer effect as a fundamental design constraint rather than an abstract theoretical curiosity. Quantum bits, or qubits, must be isolated from environmental observations that would cause decoherence and destroy their quantum properties. At the same time, the system must allow precise control over when and how quantum measurements are performed to implement quantum algorithms and extract computational results. This delicate balance between isolation and control represents one of the greatest challenges in quantum engineering. The observer effect becomes a practical consideration that determines whether quantum devices can maintain their quantum properties long enough to perform useful computations. Success requires understanding observation not as a philosophical concept, but as a physical process that can be engineered and optimized. The observer effect also plays a crucial role in quantum communication and cryptography. Quantum key distribution protocols rely on the fact that any attempt to intercept and observe quantum information necessarily disturbs it in detectable ways. This provides a physical guarantee of security that cannot be achieved with classical communication methods. The act of eavesdropping becomes synonymous with observation, making it impossible for adversaries to gain information without revealing their presence. As we delve deeper into the implications of the observer effect, we encounter questions that challenge not only our understanding of physics, but our conception of existence itself. If observation participates in creating reality, what does this mean for the universe before conscious observers evolved? How can we understand the billions of years of cosmic history that preceded the emergence of life and consciousness? These questions force us to confront the possibility that the universe before consciousness might have existed in a fundamentally different state than the classical reality we observe today. Some interpretations suggest that the early cosmos remained suspended in quantum superposition for billions of years, with no mechanism available to collapse the wave functions of stellar formation, planetary accretion, and chemical evolution into definite outcomes. This scenario paints a picture of a universe fill, stars that might have formed, galaxies that could have collided, and planets with ghostly possibilities rather than actualized events that potentially harbored the conditions for life, all existing simultaneously in quantum limbo until the first conscious observers emerged to witness them into existence. But this raises an even more disturbing paradox. If conscious observation is required to collapse quantum states into classical reality, how did consciousness itself evolve from quantum systems that had never been observed? The emergence of life and awareness would seem to require a universe with definite chemical properties, stable planetary environments, and consistent physical laws. Yet these prerequisites might not have existed in definite form until consciousness appeared to observe them. One resolution to this paradox involves what physicists call decoherence, a process by which quantum systems lose their superposition properties through interaction with their environment. Even without conscious observers, quantum systems constantly interact with surrounding particles, radiation, and fields. These environmental interactions effectively perform measurements on quantum systems, causing them to behave more like classical objects. Decoherence suggests that the universe could have developed classical properties through purely physical processes without requiring conscious intervention. The boundary between quantum and classical behavior emerges naturally from the complexity of environmental interactions rather than depending on the special properties of consciousness. Yet, decoherence doesn't completely solve the observer problem. While it explains how quantum systems can appear classical without conscious observation, it doesn't address the fundamental question of what determines which possibilities become real during the decoherence process. The mathematics of decoherence describes the suppression of quantum interference, but it doesn't specify which branch of the quantum superposition actually manifests as observed reality. This limitation has led some physicists to embrace even more radical interpretations of quantum mechanics. The many worlds interpretation, pioneered by Hugh Everett III, eliminates the need for wave function collapse entirely by proposing that all possible outcomes of quantum measurements actually occur in parallel universes. In the many worlds view, the observer effect doesn't create reality by selecting one possibility from many. Instead, it determines which branch of an infinitely splitting multiverse we experience as conscious beings. When a photon encounters the double-slit apparatus, it doesn't choose to behave as either a wave or a particle. Rather, the universe splits into multiple branches, with wave-like behavior in some branches and particle-like behavior in others. From this perspective, consciousness doesn't collapse quantum states but simply follows one path through an ever-branching tree of realities. The observer effect becomes an artifact of our limited perspective as beings confined to a single branch of the multiverse. We perceive definite outcomes not because observation creates them, but because we can only experience one possibility at a time from the vast ensemble of parallel realities. The many worlds interpretation preserves the deterministic evolution of quantum systems while explaining the apparent randomness of measurement outcomes. Every possibility predicted by quantum mechanics actually occurs somewhere in the multiverse, making quantum mechanics a completely predictive theory rather than one that relies on fundamental randomness. However, this interpretation comes with staggering ontological costs. The multiverse would contain an infinite number of copies of every conscious being, experiencing all possible variations of their lives simultaneously. Every quantum measurement would spawn countless new universes, creating an exponentially growing collection of parallel realities that can never interact with each other. Critics argue that the many worlds interpretation is untestable and therefore unscientific. If we can never observe other branches of the multiverse, how can we verify their existence? The interpretation might solve the measurement problem, but it does so by postulating an infinite collection of unobservable universes, raising questions about whether this constitutes a scientific explanation or merely a mathematical device. Despite these concerns, the many worlds interpretation has gained significant support among physicists and cosmologists who find its logical consistency appealing. It eliminates the need for mysterious collapse mechanisms while preserving the mathematical structure of quantum mechanics in its pure form. From this view, the observer effect represents not a fundamental mystery, but simply our limited perspective on a much larger reality. The debate between different interpretations of quantum mechanics reflects deeper philosophical questions about the nature of scientific explanation and the role of observation in the observer effect means for our understanding of reality theory. Each interpretation offers a different answer to what, consciousness, and the structure of the universe. Some physicists have proposed that the solution might lie in developing new experimental approaches that can distinguish between different interpretations. Advanced quantum technologies might eventually allow us to probe the measurement process with unprecedented precision, revealing whether wave function collapse represents a real physical process or merely an effective description of more complex underlying dynamics. Recent experiments have begun exploring the quantum to classical transition in increasingly sophisticated ways. Researchers can now create quantum superposition states involving larger and more complex systems, pushing the boundaries of where quantum behavior gives way to classical physics. These investigations might eventually reveal whether there exists a fundamental limit to quantum superposition or whether the classical world emerges purely through decoherence and environmental interaction. The search for objective tests of different interpretations has led to proposals for experiments involving artificial intelligence systems as observers. If consciousness plays a special role in quantum measurement, then replacing human observers with sophisticated computer systems might reveal different behavior in quantum experiments. Alternatively, if the observer effect depends only on information processing capabilities rather than consciousness per se, then AI observers should produce identical results to human observers. These experimental approaches represent attempts to transform philosophical debates about consciousness and reality into empirical questions that can be resolved through careful measurement. However, the results might not provide clear answers, as different interpretations can often make identical predictions for experimental outcomes while differing in their fundamental assumptions about the nature of reality. The observer effect has also inspired investigations into the relationship between quantum mechanics and information theory. Wheeler's it from bit hypothesis suggests that information processing, rather than matter or energy, might be the fundamental substrate of physical reality. From this perspective, the observer effect represents the mechanism by which abstract information becomes concrete physical experience. Information theoretic approaches to quantum mechanics focus on the flow and processing of information during measurement rather than the collapse of wave functions or the splitting of universes. These approaches suggest that reality emerges from networks of information exchange, with conscious observers representing particularly sophisticated information processing systems that can create complex internal models of their environment. The information perspective offers new ways to understand the observer effect that don't require choosing between consciousness-based interpretations and purely physical mechanisms. Instead, consciousness might represent a particular type of information processing that interacts with quantum systems in ways that produce the phenomena we associate with observation and measurement. This framework also connects quantum mechanics to broader questions in cognitive science and artificial intelligence about the nature of consciousness and its relationship to information processing. If consciousness emerges from sufficiently complex information integration, then the boundary between conscious and unconscious observers might be more fluid than traditional interpretations suggest. The practical implications of these theoretical developments extend into emerging technologies that rely on quantum effects for their operation. Quantum sensors, for example, exploit the sensitivity of quantum systems to environmental disturbances to achieve measurement precision that exceeds classical limits. Understanding the observer effect becomes crucial for designing sensors that can extract maximum information from quantum systems while minimizing the disturbance caused by the measurement process itself. Similarly, quantum communication protocols rely on the observer effect to detect eavesdropping attempts and ensure secure information transfer. The fundamental connection between observation and disturbance in quantum mechanics provides a physical foundation for cryptographic security that cannot be achieved through mathematical complexity alone. As quantum technologies mature from laboratory curiosities into practical devices, the observer effect transforms from an abstract philosophical puzzle into a concrete engineering constraint. The success of quantum computers, quantum sensors, and quantum communication systems depends on precise control over when, how, and what types of observations are performed on quantum systems. This technological imperative has driven the development of increasingly sophisticated theoretical frameworks for understanding quantum measurement. Modern approaches often focus on the dynamics of information flow and the emergence of classical behavior from quantum foundations rather than debating the fundamental nature of reality or consciousness. Yet the philosophical questions raised by the observer effect refuse to disappear entirely. As we develop more powerful quantum technologies and probe deeper into the foundations of quantum mechanics, we continue to encounter phenomena that challenge our basic assumptions about the relationship between observers and the reality they observe. The observer effect stands as one of the most profound mysteries in modern science, connecting the abstract mathematics of quantum theory to fundamental questions about consciousness, reality, and our place in the universe. Whether it reveals something deep about the nature of existence or simply reflects the limitations of our current theoretical understanding, it continues to inspire new experiments, new interpretations, and new ways of thinking about the relationship between mind and world. As we push further into the quantum realm, developing technologies that exploit the strange properties of superposition and entanglement, we are forced to grapple more directly with the implications of the observer effect for our understanding of reality itself. The questions it raises about the role of observation in physical processes may ultimately require us to reconsider not just our theories of quantum mechanics, but our entire conception of what it means to exist in a universe where the act of looking might literally help create what we see. The journey into quantum mechanics has revealed that reality might be far stranger and more participatory than we ever imagined. As we continue to explore these mysteries, we find ourselves not merely discovering the universe, but perhaps participating in its ongoing creation through the very questions we choose to ask and the observations we decide to make. The implications become even more unsettling when we consider what happens at the moment of quantum measurement itself. Picture the exact instant when a photon hits a detector screen after passing through the double-slit apparatus. In that infinitesimally brief moment, something unprecedented occurs in the fabric of reality. The wave function, which had been describing all possible paths the photon might take, suddenly collapses into a single definite outcome. One specific location on the screen registers the photon's arrival, while all other possibilities vanish as if they had never existed. This collapse happens faster than light can travel, faster than any known physical process can propagate information. The wave function doesn't gradually transition from multiple possibilities to a single reality. It jumps discontinuously via other aspect of quantum mechanics. Theta, the smooth evolution that governs every Schrödinger equation, which perfectly describes how quantum systems evolve over time, simply stops working at the moment of measurement. This mathematical breakdown points to something profound about the nature of reality itself. Either our equations are fundamentally incomplete, missing some crucial piece of physics that governs the measurement process, or measurement represents a truly non-physical phenomenon that operates outside the normal laws of quantum mechanics. Neither possibility is comforting for our scientific worldview. The measurement problem becomes even more perplexing when we examine what happens to the information contained in quantum superposition states. Before measurement, a single photon in the double-slit experiment contains information about traveling through both slits simultaneously. This information is real and measurable through the interference patterns it creates. But when we observe which slit the photon passes through, this information doesn't just become hidden or inaccessible, it appears to be destroyed completely and irreversibly. This destruction of information violates one of the most fundamental principles in physics. The conservation of information is as basic to our understanding of reality as the conservation of energy or momentum. Yet quantum measurement seems to routinely violate this principle, erasing quantum information in ways that should be impossible according to our deepest theories about how the universe works. Some physicists have proposed that the information isn't actually destroyed, but rather becomes inaccessible to us as conscious observers. In this view, the full quantum information remains encoded in correlations between the measured system and its environment, but these correlations become so complex and widespread that they cannot be reconstructed by any practical means. The information exists, but is effectively lost in the quantum noise of environmental interactions. This perspective connects to the concept of quantum decoherence, which describes how quantum systems lose their coherent superposition properties through interaction with their surroundings. Every quantum system is constantly bombarded by photons, surrounded by air molecules, and coupled to electromagnetic fields. These environmental interactions act like continuous weak measurements, gradually extracting information about the system's quantum state and spreading it throughout the environment. Decoherence explains why we never observe quantum superposition effects in everyday objects despite their being made of quantum particles. A baseball thrown through the air interacts with trillions of air molecules, each interaction slightly measuring its position and momentum. These countless micro-measurements destroy the quantum coherence that would be necessary for the baseball to exist in multiple locations simultaneously. The baseball appears classical, not because it is fundamentally different from quantum particles, but because its quantum properties are constantly being measured and destroyed by environmental interactions. But decoherence alone doesn't solve the measurement problem. It explains why quantum effects become invisible in macroscopic systems, but it doesn't address the fundamental question of what determines which specific outcome occurs during a measurement. When a photon's wave function collapses to a single location on a detector screen, decoherence can explain why the photon doesn't continue to exist in multiple locations, but it cannot predict which location will be chosen. The randomness of quantum measurement outcomes represents another challenge to our understanding of physical reality. Unlike classical physics, where identical initial conditions always produce identical results, quantum mechanics appears to involve fundamental randomness that cannot be reduced to hidden variables or incomplete knowledge. Two identical photons prepared in exactly the same quantum state will still produce different measurement outcomes with probabilities determined by the quantum wave function. Einstein famously objected to this fundamental randomness, declaring that God does not play dice with the universe. He believed that quantum mechanics must be incomplete, missing some hidden variables that would restore determinism to physics if they could be discovered. Along with colleagues Boris Podolsky and Nathan Rosen, Einstein proposed a thought experiment designed to demonstrate that quantum mechanics could not be a complete description of physical reality. The EPR paradox, as it came to be known, involved pairs of particles that become quantum entangled, meaning their properties remain correlated even when separated by vast distances. Einstein argued that if quantum mechanics were complete, measuring one particle would instantaneously affect its distant partner, violating the principle that information cannot travel faster than light. He concluded that the particles must possess predetermined properties that are hidden from quantum mechanical description. For decades, the EPR paradox remained a philosophical debate rather than an experimental question. The technology needed to test Einstein's hidden variable theories didn't exist, leaving physicists to argue about the interpretation of quantum mechanics based on theoretical considerations alone. But in the 1960s, physicist John Stuart Bell developed a mathematical framework that could distinguish between quantum mechanics and hidden variable theories through experimental measurement. Bell's theorem proved that any theory based on local hidden variables must satisfy certain mathematical inequalities. These Bell inequalities set limits on the correlations that can exist between measurements performed on separated particles if those particles possess predetermined properties that are independent of the measurement process. Quantum mechanics, on the other hand, predicts correlations that violate Bell's inequalities under specific experimental conditions. The first decisive tests of Bell's inequalities were performed in the 1970s and 1980s, with increasingly sophisticated experiments confirming the quantum mechanical predictions. These results demonstrated that either the universe involves fundamental non-locality, with instantaneous connections between distant particles, or it lacks objective reality in the sense Einstein assumed. Either possibility challenges our basic assumptions about the nature of physical reality. The violation of Bell's inequalities provides some of the strongest evidence that the observer effect reflects something fundamental about reality, rather than simply revealing limitations in our measurement techniques. If particles possessed definite properties independent of observation, as Einstein believed, then the correlations between distant measurements should satisfy Bell's mathematical constraints. The fact that they don't suggests that the act of observation genuinely participates in determining what becomes real. Modern experiments have closed virtually every loophole that might allow hidden variable theories to explain the violation of Bell's inequalities. Researchers have performed measurements on particles separated by distances so large that light signals cannot travel between them during the measurement process, eliminating the possibility of any communication between the measurement devices. They have used random number generators to choose which properties to measure, preventing any predetermined correlations from influencing the results. These loophole-free Bell tests provide compelling evidence that quantum entanglement involves genuine non-locality, with measurement outcomes on one particle instantaneously influencing the correlations observed on its distant partner. This quantum non-locality does suggest that the universe is faster than light communication, but more fundamentally interconnected than classical locality, and the observer effect paints a picture of reality that connected through quantum entanglement, with measurements everyday experience suggests. Distant particles remain is both more unified and more dependent on observation than our physics assumed. The combination of quantum non-on-one affecting the possibilities available to others. The act of observation doesn't just reveal pre-existing properties, but participates in a cosmic dance of correlation and possibility that spans the entire universe. Some interpretations of quantum mechanics embrace this interconnectedness as evidence for a holistic view of reality. Instead of thinking of the universe as composed of separate objects with independent properties, quantum mechanics suggests that reality consists of an interconnected web of relationships that become definite only through acts of observation. From this perspective, individual particles don't possess inherent properties, but rather exist as nodes in a network of quantum correlations that spans all of space and time. This holistic interpretation connects to ancient philosophical traditions that viewed reality as fundamentally interconnected rather than composed of separate, independent entities. The quantum mechanical description of entangled particles echoes the Buddhist concept of dependent origination, which holds that all phenomena arise in dependence upon causes and conditions rather than existing independently. Similarly, the observer effect resonates with idealistic philosophical traditions that emphasize the role of consciousness in constructing experienced reality. However, most contemporary physicists resist drawing direct connections between quantum mechanics and philosophical or spiritual traditions. They prefer to focus on the mathematical formalism and experimental predictions of quantum theory rather than speculating about its broader implications for the nature of reality or consciousness. This scientific conservatism reflects both the success of quantum mechanics as a practical theory and the difficulty of translating its mathematical abstractions into intuitive concepts. The practical success of quantum mechanics has been extraordinary, leading to technologies that have transformed human civilization. Lasers, transistors, computer chips, and magnetic resonance imaging all depend on quantum mechanical effects for their operation. The theory has enabled precise predictions about atomic structure, chemical bonding, and material properties that have revolutionized our understanding of matter at its most fundamental level. This technological success provides strong evidence that quantum mechanics captures something essential about the nature of reality, even if we struggle to understand what that something actually is. The observer effect isn't just a philosophical curiosity, but a practical consideration that determines how quantum devices function in the real world. Engineers must account for the role of measurement and observation when designing quantum systems, making the observer effect a concrete engineering constraint rather than an abstract theoretical puzzle. The development of quantum computers has brought the observer effect into sharp, practical focus. These devices rely on maintaining quantum superposition states in their computational elements, while carefully controlling when and how observations are made to extract computational results. The challenge lies in preserving the quantum properties needed for computation, while still allowing the controlled measurements necessary to read out the final answers. Quantum error correction represents one of the most sophisticated attempts to manage the observer effect in practical devices. These techniques use redundant encoding of quantum information across multiple physical systems to protect against the decoherence that would otherwise destroy quantum computational states. The error correction process involves continuous monitoring of the quantum system to detect and correct errors without directly observing the computational information itself. This careful balance between observation and non-observation requires a deep understanding of how different types of measurement affect quantum systems. Some measurements destroy quantum coherence entirely, while others can extract limited information without completely collapsing superposition states. The design of quantum computers depends on exploiting these subtle distinctions to create devices that can harness quantum effects while remaining sufficiently isolated from unwanted observations. The success of quantum error correction demonstrates that the observer effect can be controlled and manipulated through careful engineering, even if its fundamental nature remains mysterious. This practical mastery of quantum measurement has enabled the construction of quantum computers with hundreds of quantum bits, bringing us closer to the point where quantum devices might solve problems that are intractable for classical computers. But even as we learn to engineer quantum systems with increasing sophistication, the fundamental questions raised by the observer effect remain unresolved. The practical success of quantum mechanics doesn't eliminate the conceptual puzzles about what observation means or how it relates to consciousness and reality. Instead, it makes these questions more urgent by demonstrating that the observer effect has real consequences for the technologies that are reshaping our world. The quantum internet represents another frontier where the observer effect plays a crucial role. This emerging technology aims to connect quantum computers and other quantum devices through networks that can transmit quantum information while preserving its delicate quantum properties. The challenge lies in detecting and correcting errors in quantum communication channels without directly observing the quantum information being transmitted. Quantum key distribution already demonstrates how the observer effect can be harnessed for practical cryptographic applications. These systems exploit the fact that any attempt to intercept quantum information necessarily disturbs it in detectable ways, providing a physical guarantee of security that cannot be achieved through mathematical complexity alone. The act of eavesdropping becomes synonymous with observation, making it impossible for adversaries to gain information without revealing their presence. As quantum technologies mature and become more widely deployed, society will need to grapple with the implications of living in a world where the act of observation consequences. Privacy has measurable physical security, and even our conception of objective reality may need to be reconsidered in light of quantum mechanical insights about the relationship between observers and the systems they observe. The observer effect also raises profound questions about the nature of scientific knowledge itself. If reality depends on observation in fundamental ways, what does this mean for the scientific method, which is based on objective measurement and reproducible results? How can we maintain scientific objectivity if the act of observation participates in creating the phenomena we study? These epistemological questions become particularly acute in fields like quantum biology, where researchers investigate whether quantum effects play important roles in living systems. The study of quantum coherence in biological processes faces the challenge that the very act of measurement might disrupt the delicate quantum states that evolution has learned to exploit. Observing quantum effects in living systems might be like trying to study a soap bubble by poking it with a stick. Recent discoveries of quantum effects in photosynthesis, bird navigation, and possibly even consciousness itself suggest that biology has found ways to harness quantum mechanics for functional purposes. But studying these effects requires extremely sensitive measurements that threaten to destroy the very phenomena being investigated. The observer effect becomes a practical limitation on our ability to understand how life exploits quantum mechanics. The relationship between quantum mechanics and consciousness remains one of the most speculative and controversial areas of research. Some scientists propose that the brain might use quantum effects for information processing, possibly explaining the unity of conscious experience or the apparent non-algorithmic aspects of human cognition. Others argue that the warm, wet, noisy environment of the brain would destroy quantum coherence too quickly for it to play any functional role. The debate over quantum consciousness reflects deeper uncertainties about the nature of consciousness itself and its relationship to physical processes. If consciousness emerges from complex information processing in the brain, as most neuroscientists believe, then it might not require any special quantum mechanical effects. But if consciousness involves something more fundamental than classical computation, then quantum mechanics might provide the additional ingredients needed to bridge the gap between subjective experience and objective physical processes. The observer effect continues to challenge our understanding of the relationship between subjective experience and objective reality. Whether consciousness plays a special role in quantum measurement or not, the fact remains that all of our knowledge about quantum mechanics comes through conscious observation of experimental results. We never directly experience quantum superposition states ourselves, only their classical consequences as recorded by measuring instruments and interpreted by conscious minds. This limitation raises questions about whether we can ever truly understand quantum mechanics or whether we are forever trapped in a classical perspective that can only observe the shadows of quantum reality. The observer effect might represent not just a feature of quantum mechanics, but a fundamental limitation on what any conscious being can know about the nature of reality itself. As we push deeper into the quantum realm, developing more sophisticated technologies and exploring more subtle effects, we continue to encounter phenomena that challenge our basic assumptions about observation, measurement, and reality. The observer effect stands as a persistent reminder that the universe might be far stranger and more participatory than our classical intuitions suggest, forcing us to question not just our theories about quantum mechanics, but our entire conception of what it means to observe and know the world around us. The implications of quantum measurement extend far beyond laboratory experiments into realms that challenge our most basic assumptions about the nature of time itself. Consider what happens when we examine the precise moment a quantum measurement occurs. The collapse from superposition to definite outcome doesn't unfold gradually like other physical processes. It happens instantaneously, violating our normal understanding of temporal sequence and causation. This instantaneous collapse creates what physicists call the measurement problem's temporal paradox. If wave function collapse represents a real physical process, it must occur faster than light can travel across the quantum system being measured. For microscopic particles, this might seem insignificant, but quantum superposition states can be created across macroscopic distances, spanning meters or even kilometers. When these extended quantum states collapse, the coordination required between distant parts of the system appears to violate the fundamental principle that nothing can travel faster than light. The resolution of this paradox has led some physicists to question whether wave function collapse represents a real physical process at all. Perhaps what we interpret as instantaneous collapse actually reflects our limited understanding of how quantum information flows through complex systems. The appearance of instantaneous change might emerge from correlations that were established earlier in the system's history, similar to how breaking one pencil in a pair of connected pencils instantly affects both pieces without requiring faster-than-light communication. This perspective connects to the block universe interpretation of space-time, where past, present, and future exist simultaneously as different regions of four-dimensional space-time. In this view, quantum correlations extend not just across space but across time, creating connections between measurement events that appear separate from our temporal perspective but are unified in the deeper structure of space-time itself. The temporal aspects of quantum measurement become even more mysterious when we examine quantum tunneling phenomena. Particles can pass through energy barriers that should be impossible to cross according to classical physics, appearing on the other side without spending any measurable time inside the barrier region. The tunneling process seems to occur instantaneously, raising questions about whether quantum particles can move through space without traversing the intervening distance. Recent experiments have attempted to measure the tunneling time by examining how long particles spend inside barrier regions. These investigations reveal something even stranger than instantaneous tunneling. The measurements suggest that particles can emerge from barriers before they finish entering them, creating a pattern to violate cause-negative transit times that see mality itself. These temporal anomalies don't allow faster-than-light communication or true time travel, but they reveal that quantum mechanics operates according to temporal principles that differ fundamentally from our classical expectations. The act of measurement appears to select not just which spatial outcome occurs, but which temporal sequence becomes real from the quantum superposition of different possible histories. The relationship between quantum measurement and time becomes particularly important for understanding the early universe. Cosmological models based on quantum mechanics must grapple with what happened before the first measurements collapsed, primordial quantum states into the classical structures we observe today. If the universe began in a quantum superposition of different possible configurations, what triggered the first measurement that began the process of classical reality formation? Some cosmological theories propose that quantum fluctuations in the early universe underwent a process called spontaneous symmetry breaking, where quantumed into definite configurations, superposition states collapse without requiring external observation. This process would have occurred throughout space as the expanding universe cooled below critical temperatures, creating the large stars and planets. But scale structure that eventually gave rise to galaxies, spontaneous symmetry breaking doesn't eliminate the measurement problem. It simply pushes the question deeper by asking what determined which symmetry-breaking pattern occurred from the vast ensemble of quantum possibilities. The early universe faced the same fundamental choice between different potential realities that individual quantum particles encounter during measurement of spacetime itself. The many, but on a cosmic scale involving the structure world's interpretation, offers one resolution by proposing that all possible symmetry-breaking patterns actually occurred, creating parallel universes with different physical laws and cosmic structures. Our observed universe represents just one branch of an infinite multiverse where every quantum possibility became real somewhere. The apparent uniqueness of our cosmic history would be an artifact of our limited perspective rather than evidence for a special selection mechanism. Alternative approaches focus on the role of gravity in quantum measurement. General relativity describes gravity not as a force but as the curvature of spacetime itself, suggesting that gravitational effects might operate differently from other quantum phenomena. Some theories propose that sufficiently strong gravitational fields can collapse quantum superposition states through purely geometric effects, providing a natural mechanism for measurement that doesn't require conscious observers or environmental decoherence. These gravitational approaches to the measurement problem predict that quantum superposition states become increasingly unstable as systems become more massive. Microscopic particles can maintain superposition indefinitely in perfect isolation, but macroscopic objects would spontaneously collapse to definite states due to their gravitational self-interaction. This would explain why we never observe quantum effects in everyday objects without requiring any special role for consciousness or measurement apparatus. Experimental tests of gravitational collapse theories require creating quantum superposition states with increasingly massive objects to determine whether gravity does indeed limit quantum coherence. Recent experiments have achieved superposition states with molecules containing thousands of atoms, pushing toward the mass scales where gravitational effects might become significant. Future experiments aim to test quantum coherence in microscopic diamonds and other massive objects that approach the theoretical limits of quantum behavior. The intersection of quantum mechanics and general relativity also raises questions about the nature of spacetime itself during quantum measurements. If quantum systems can exist in superposition states before measurement, what happens to the spacetime geometry around these systems? Does spacetime also exist in superposition with different geometric configurations corresponding to different measurement outcomes? These questions become where quantum effects, and particularly relevant for understanding black holes' gravitational phenomena, reach their most extreme values. The information paradox of black hole evaporation involves questions about what happens to quantum information that falls into black holes and whether it can be recovered through Hawking radiation. The resolution of this paradox might require understanding how quantum measurement works in the presence of extreme gravitational fields. String theory and other approaches to quantum gravity suggest that spacetime itself might be an emergent property that arises from more fundamental quantum processes. In these theories, the familiar three dimensions of space and one dimension of time emerge from the collective behavior of quantum degrees of freedom that exist in higher dimensional spaces. The observer effect might reflect the mechanism by which these fundamental quantum processes give rise to the classical space-time geometry we experience. The holographic principle, derived from black hole physics, proposes that all the information in a volume of space can be encoded on its two-dimensional boundary surface. This principle suggests that our three-dimensional experience of reality might be a projection from information stored on a distant boundary, similar to how a hologram creates three-dimensional images from two-dimensional patterns. The observer effect could represent the process by which boundary information becomes decoded into the three-dimensional reality we observe. These holographic models of reality offer new perspectives on the measurement problem by suggesting that quantum states and their collapse might be more fundamental than the space-time arena in which we observe them. The act of measurement might not occur within space-time, but rather at the boundary level where the holographic encoding takes place. Our experience of measurement as occurring at specific locations and times would be a projection from these more fundamental boundary processes. The implications extend into practical applications where the observer effect intersects with emerging technologies. Quantum sensing devices exploit the extreme sensitivity of quantum systems to environmental disturbances to achieve measurement precision that surpasses classical limits. These devices must carefully balance the competing requirements of maintaining quantum coherence while still extracting useful information from the system being measured. Gravitational wave detectors represent one of the most sophisticated applications of quantum sensing principles. These devices use laser interferometry to detect tiny distortions in space-time caused by passing gravitational waves. The measurements are so precise that quantum fluctuations in the laser light itself become a limiting factor, requiring sophisticated quantum control techniques to achieve the sensitivity needed to detect gravitational waves from distant cosmic events. The success of gravitational wave astronomy demonstrates how understanding and controlling the observer effect enables measurements that would have seemed impossible just decades ago. The detection of gravitational waves from black hole mergers and neutron star collisions has opened an entirely new window on the universe, revealing cosmic phenomena that are invisible to traditional electromagnetic observations. Quantum clocks represent another frontier where the observer effect plays a crucial role in advancing measurement precision. These devices use the quantum properties of atomic transitions to achieve timekeeping accuracy that surpasses conventional atomic clocks by orders of magnitude. The extreme precision requires careful control of how quantum measurements are performed to extract timing information while preserving the quantum coherence needed for enhanced sensitivity. The development of quantum sensor networks promises to revolutionize our ability to probe fundamental physics by correlating measurements across multiple quantum devices. These networks could enable tests of general relativity and quantum mechanics with unprecedented precision, potentially revealing deviations from current theories that point toward new physics. The observer effect becomes a design consideration for determining how to extract maximum information from distributed quantum measurements while maintaining the correlations needed for enhanced sensitivity. Biological systems present unique challenges for understanding the observer effect because living organisms have evolved to exploit quantum mechanics in ways that remain largely mysterious. Photosynthesis in plants and bacteria involves quantum coherence effects that enhance energy transfer efficiency, but these effects operate in warm, wet environments that should rapidly destroy quantum coherence according to conventional understanding. The study of quantum effects in biology requires measurement techniques that can probe quantum coherence without destroying it, pushing the limits of what's possible with current technology. Researchers must develop increasingly sophisticated methods for distinguishing genuine quantum effects from classical phenomena that might mimic quantum behavior in complex biological systems. Recent discoveries suggest that quantum effects might play important roles in other biological processes, including enzyme catalysis, DNA mutation, and possibly even consciousness itself. But studying these effects faces the fundamental challenge that the act of measurement might disrupt the very phenomena being investigated. The observer effect becomes both the key to understanding quantum biology and the primary obstacle to studying it. The relationship between quantum mechanics and consciousness remains one of the most speculative areas of research, but it raises profound questions about the nature of subjective experience and its relationship to physical processes. Some theories propose that consciousness emerges from quantum processes in microtubules within neurons, while others suggest that quantum mechanics might be necessary to explain the apparent non-algorithmic aspects of human cognition. Whether or not consciousness involves special quantum effects, the fact remains that our entire understanding of quantum mechanics comes through conscious observation of experimental results. We never directly experience quantum superposition states ourselves, only their consequences as recorded by classical measuring devices and interpreted by conscious minds. This creates a fundamental epistemological puzzle about the relationship between subjective experience and objective physical processes. The observer effect might represent not just a feature of quantum mechanics, but a fundamental limitation on what any conscious being can know about reality. Our classical experience of definite objects with specific properties might be a necessary simplification that allows conscious minds to navigate a quantum world that is far more complex and interconnected than our intuitive understanding suggests. As quantum technologies become more sophisticated and widespread, society will need to grapple with living in a world where the act of observation has measurable consequences for the phenomena being observed. This might require reconsidering basic assumptions about privacy, security, and even the nature of objective truth in contexts where quantum effects become relevant to everyday experience. The observer effect challenges us to think more carefully about the relationship between knowledge and reality, between what we can measure and what actually exists. As we develop increasingly powerful tools for probing the quantum world, we must remember that our observations are not passive recordings of pre-existing facts, but active participations in the ongoing creation of the reality we experience. The journey into quantum mechanics has revealed that the universe might be far more strange, interconnected, and dependent on observation than our classical intuitions suggest. The observer effect stands as a persistent reminder that reality and consciousness might be more intimately connected than we ever imagined, forcing us to question not just our theories about quantum mechanics, but our entire understanding of what it means to exist in a universe where the very act of looking might help determine what we see. The quantum realm reveals another disturbing truth about the nature of reality when we examine what physicists call quantum entanglement. Einstein called it spooky action at a distance, and for good reason. When two particles become entangled, measuring one instantly affects the other, regardless of how far apart they are. This isn't just correlation. This is something far more unsettling. Imagine two coins that are quantum entangled. When you flip one and it lands heads, the other immediately lands tails, even if it's on the other side of the galaxy. The measurement of the first coin doesn't just reveal its state, it instantaneously determines the state of its partner through some mechanism that operates faster than light itself. But here's where it gets truly bizarre. Before you measure either coin, both exist in superposition states, simultaneously heads and tails. The act of measuring one coin doesn't just collapse its own wave function, it collapses the wave function of its distant partner, forcing both particles to choose definite states from their quantum possibilities. This suggests that reality operates as an interconnected web rather than a collection of separate objects. The observer effect isn't limited to individual systems. It extends across space through invisible quantum connections that bind distant parts of the universe together in ways that classical physics never imagined possible. Recent experiments have tested these quantum connections with increasing sophistication. Scientists have entangled particles across distances of hundreds of kilometers, then performed measurements that violate the fundamental limits that classical physics imposes on correlations between distant events. These violations provide compelling evidence that observation participates in creating reality not just locally, but across the entire fabric of space-time. The implications become even more disturbing when we consider the temporal aspects of quantum entanglement. Some experiments suggest that entangled particles can be created across time as well as space. A measurement performed today might become entangled with a measurement that won't occur until tomorrow, creating correlations that span past, present, and future simultaneously. This understanding of causation and free temporal entanglement challenges our basic will. If future measurements are already correlated with past events through quantum connections, what does this mean for our ability to make independent choices about what to observe? The observer effect might operate not just in the present moment, but across the entire timeline of cosmic history. Wheeler's delayed choice experiments push these temporal paradoxes to their logical extreme. In these sophisticated setups, the decision about whether to perform a measurement can be made after the quantum system has already passed through the experimental apparatus. Remarkably, this delayed choice appears to retroactively determine how the system behaved during its earlier journey through the equipment. The results suggest that future observations can reach backward in time to influence past events. The quantum system seems to know about measurement decisions that haven't been made yet, adjusting its behavior accordingly. This apparent retrocausality doesn't allow practical time travel or communication with the past, but it reveals that the observer effect operates according to temporal principles that violate our normal understanding of cause and effect. Most physicists interpret these experiments in terms of correlations rather than actual backward time travel. The quantum system doesn't really change its past behavior based on future measurements. Instead, the correlations between different parts of the experiment exist timelessly in the quantum description, becoming manifest only when measurements reveal the relationships between events separated in time. But even this more conservative interpretation has profound implications for our understanding of reality. It suggests that the observer effect doesn't create reality moment by moment, but rather selects which correlations become manifest from a timeless quantum description that encompasses all possible measurement outcomes simultaneously. This perspective connects to the block universe interpretation of space-time, where past, present, and future exist as equally real regions of four-dimensional space-time. In this view, the observer effect might not determine what happens, but rather which slice of the eternal block universe we experience as conscious beings moving through time. The relationship between consciousness and time in quantum mechanics raises questions that push beyond physics into philosophy and cognitive science. Our subjective experience of temporal flow, where the future becomes present and then recedes into the past, might not reflect fundamental properties of time itself, but rather the way conscious minds process information about quantum correlations. Some theories propose that consciousness creates the illusion of temporal flow by constantly selecting which quantum possibilities become experiential reality. Each moment of conscious observation would represent a choice point where infinite quantum possibilities collapse into a single experienced outcome, creating the stream of definite events that we interpret as the passage of time. This consciousness-based view of temporal flow suggests that time might not exist independently of conscious observers. The universe might consist of timeless quantum correlations that become organized into temporal sequences only through the measurement processes associated with conscious observation. Reality would exist as pure potential until consciousness arrives to observe it into temporal existence. Alternative approaches focus on information theory and computation rather than consciousness per se. These frameworks suggest that the arrow of time emerges from the processing of information rather than from conscious observation specifically. Any system capable of recording and processing information about quantum states would contribute to the temporal structure of reality, with consciousness representing just one particularly sophisticated type of information processing system. The debate over consciousness and time in quantum mechanics reflects deeper uncertainties about the nature of both phenomena. We still don't understand how consciousness arises from physical processes, making it difficult to determine whether it plays a special role in quantum measurement. Similarly, the fundamental nature of time remains mysterious, with physics offering multiple competing theories about whether temporal flow represents an objective feature of reality or a subjective artifact of how information processing systems perceive their environment. These conceptual challenges become increasingly important as we develop quantum technologies that exploit temporal aspects of quantum mechanics. Quantum computers must maintain precise control over the temporal evolution of quantum states while carefully timing when measurements are performed to extract computational results. The relationship between quantum computation and time raises practical questions about how to optimize quantum algorithms and error correction procedures. Quantum communication protocols also depend critically on timing relationships between measurements performed on entangled particles. Quantum cryptography systems must coordinate measurements across space and time to detect eavesdropping attempts and ensure secure communication. Understanding how the observer effect operates across temporal separations becomes crucial for designing robust quantum communication networks. The practical applications of quantum mechanics force us to treat the observer effect as an engineering constraint rather than just a philosophical puzzle. Quantum sensors, quantum computers, and quantum communication systems all require precise control over when, how, and what types of observations are performed on quantum systems. The success of these technologies depends on our ability to harness the observer effect while minimizing its disruptive consequences. This technological imperative has driven the development of increasingly sophisticated theoretical frameworks for understanding quantum measurement. Modern approaches often focus on information theory, decoherence, and the emergence of classical behavior from quantum foundations rather than debating the fundamental role of consciousness in physical reality. Yet the philosophical questions refuse to disappear entirely. As quantum technologies become more powerful and widespread, we encounter new phenomena that challenge our basic assumptions about observation and reality. The practical success of quantum mechanics doesn't resolve the conceptual puzzles, but rather makes them more urgent by demonstrating that the observer effect has real consequences for the world we inhabit. The development of artificial intelligence systems raises particularly intriguing questions about the nature of observation and consciousness in quantum mechanics. If consciousness plays a special role in quantum measurement, then replacing human observers with sophisticated computer systems might reveal different behavior in quantum experiments. Alternatively, if the observer effect depends only on information processing capabilities rather than consciousness per se, then AI observers should produce results identical to human observers. These questions become increasingly relevant as AI systems become more sophisticated and begin to participate directly in scientific research and quantum technology development. Machine learning algorithms already play crucial roles in analyzing quantum experimental data and optimizing quantum device performance. As these systems become more autonomous and capable, they might begin to function as observers in quantum experiments without human intervention. The prospect of AI observers raises fundamental questions about the relationship between consciousness, intelligence, and quantum measurement. If quantum mechanics truly depends on conscious observation, then we need to understand what kinds of information processing systems qualify as conscious observers. If consciousness is not required, then we need to determine what physical properties enable systems to serve as quantum observers. Recent research in quantum biology suggests that living systems might have evolved sophisticated mechanisms for exploiting quantum effects while minimizing the disruptive consequences of observation. Photosynthesis, bird navigation, and possibly even neural processes in the brain appear to rely on quantum coherence effects that persist despite the warm, wet, noisy environments where biological systems operate. These biological quantum effects challenge our understanding of how the observer effect operates in complex, dynamic systems. Living organisms must somehow maintain quantum coherence while constantly interacting with their environment through metabolic processes, sensory input, and motor output. This requires exquisite control over which types of interactions destroy quantum coherence and which can be tolerated without disrupting quantum functionality. The study of quantum effects in biological systems also raises questions about whether evolution has discovered principles for managing the observer effect that we haven't yet understood. Billions of years of natural selection might have produced biological mechanisms for exploiting quantum mechanics that surpass our current technological capabilities. Understanding these biological quantum processes could inspire new approaches to quantum technology design. The intersection of quantum mechanics with biology, artificial intelligence, and advanced technology suggests that the observer effect might be more pervasive and important than we currently realize. Rather than being limited to exotic laboratory experiments, quantum measurement processes might play crucial roles in many natural and artificial systems that we encounter in everyday life. As we develop increasingly sophisticated tools for probing and manipulating quantum systems, we must grapple with the possibility that observation and reality are more intimately connected than classical physics suggested. The observer effect might not represent a strange quirk of quantum mechanics, but rather a fundamental principle that governs how information, consciousness, and physical reality interact at the deepest levels. The journey into quantum mechanics has revealed that the universe operates according to principles that challenge our most basic intuitions about the nature of existence. The observer effect stands as perhaps the most profound of these challenges, suggesting that reality might not exist independently of the conscious beings who observe it. Whether this reflects something deep about the relationship between mind and cosmos, or simply reveals the limitations of our current theoretical understanding, it continues to inspire new experiments, new technologies, and new ways of thinking about what it means to exist in a quantum universe. The questions raised by the observer effect extend far beyond the laboratory into fundamental issues about the nature of knowledge, reality, and our place in the cosmos. As we continue to push the boundaries of quantum science and technology, we are forced to confront the possibility that the act of observation doesn't just reveal the universe but participates in its ongoing creation. The implications of this realization may ultimately require us to reconsider not just our theories about quantum mechanics, but our entire understanding of what it means to be conscious observers in a reality that might depend on consciousness for its very existence. The quantum measurement process reveals something even more disturbing when we examine what happens to information during the collapse of superposition states. Every quantum system contains what physicists call quantum information, encoded in the precise mathematical relationships between different possible outcomes. This information isn't just abstract mathematics. It represents real physical properties that can be measured, manipulated, and used to perform calculations that are impossible with classical systems. When a quantum measurement occurs, something unprecedented happens to this information. The rich tapestry of quantum possibilities that existed before measurement doesn't simply become hidden or inaccessible. It appears to be completely erased from reality, as if those other possibilities never existed at all. This destruction of information violates one of the most fundamental principles in physics, the conservation of information, which states that information can be transformed but never truly destroyed. Think about what this means for a moment. Before measurement, a single photon passing through the double-slit experiment contains complete information about traveling through both paths simultaneously. This information is real enough to create measurable interference patterns and perform quantum computations. But the instant we observe which slit the photon passes through, all information about the other possibility vanishes instantly and irreversibly. This erasure of quantum information creates what some physicists call the information paradox of quantum measurement. If information truly cannot be destroyed, then either our understanding of quantum measurement is fundamentally flawed, or the information is somehow preserved in ways we cannot detect. Some theories propose that the missing information becomes encoded in correlations with the environment, spreading throughout the universe in patterns too complex to reconstruct. The environmental approach to quantum measurement, known as decoherence theory, suggests that quantum systems never truly collapse, but rather become so entangled with their surroundings that the quantum effects become practically invisible. From this perspective, the information isn't destroyed, but rather distributed across so many environmental degrees of freedom that it becomes impossible to access. Imagine trying to reconstruct a shredded document by analyzing every air molecule in the room where it was destroyed. In principle, the information might still exist in the precise positions and velocities of countless particles, but extracting it would require measuring and processing more information than exists in the observable universe. The quantum information becomes effectively lost, even though it technically remains encoded in the environmental correlations. But decoherence theory faces its own conceptual challenges. While it explains how quantum effects become invisible in large systems, it doesn't address the fundamental question of what determines which specific outcome manifests during a measurement. The theory can predict the probabilities of different measurement results, but it cannot explain why one particular outcome occurs rather than another. This limitation points to a deeper mystery about the nature of randomness in quantum mechanics. Unlike classical physics, where apparent randomness typically results from incomplete knowledge about complex systems, quantum mechanics appears to involve genuine randomness that cannot be reduced to hidden variables or deterministic processes. Two identical particles prepared in exactly the same quantum state will still produce different measurement outcomes with probabilities determined by the quantum wave function. Einstein famously objected to this fundamental randomness, insisting that God does not play dice with the universe. He believed that quantum mechanics must be incomplete, missing some hidden variables that would restore determinism to physics if they could be discovered. This philosophical position led him to propose, along with colleagues Boris Podolsky and Nathan Rosen, a thought experiment designed to demonstrate that quantum mechanics could not be a complete description of physical reality. The EPR paradox involved pairs of particles that become quantum entangled, meaning their properties remain correlated even when separated by vast distances. Einstein argued that if quantum mechanics were complete, measuring one particle would instantaneously affect its distant partner, violating the principle that no influence can travel faster than light. He concluded that the particles must possess predetermined properties that quantum mechanics fails to describe. For decades, the EPR paradox remained a philosophical debate rather than an experimental question. The technology needed to test Einstein's hidden variable theories didn't exist, leaving physicists to argue about interpretations based on theoretical considerations alone. But in the 1960s, physicist John Stuart Bell developed a mathematical framework that could distinguish between quantum mechanics and hidden variable theories through actual measurements. Bell's theorem proved that any theory based on local hidden variables must satisfy certain mathematical constraints on the correlations between measurements performed on separated particles. These Bell inequalities set fundamental limits on how strongly correlated distant measurements can be if the particles possess predetermined properties that exist independently of the measurement process. Quantum mechanics, however, predicts correlations that violate Bell's inequalities under specific experimental conditions. The quantum mechanical predictions suggest that measuring one particle can instantaneously influence the measurement statistics of its distant partner in ways that exceed what any local hidden variable theory could explain. The first decisive experimental tests of Bell's inequalities were performed in the 1970s and 1980s, with increasingly sophisticated experiments confirming the quantum mechanical predictions. These results provided compelling evidence that either the universe involves genuine non-locality, with instantaneous connections between distant particles, or it lacks objective reality in the sense that Einstein assumed. Modern experiments have closed virtually every conceivable loophole that might allow classical explanations for the violation of Bell's inequalities. Researchers have performed measurements on particles separated by distances so large that light signals cannot travel between them during the measurement process, eliminating any possibility of communication between the detection apparatus. They have used quantum random number generators to choose which properties to measure, preventing any predetermined correlations from influencing the results. These loophole-free Bell tests provide overwhelming evidence that quantum entanglement involves genuine non-locality, with measurement outcomes on one particle instantaneously affecting the correlations observed on its distant partner. This quantum non-locality doesn't allow faster-than-light communication, but it reveals that the universe is more fundamentally interconnected than classical physics suggested. The combination of quantum non-locality and the observer effect paints a picture of reality that is both more unified and more dependent on observation than our everyday experience suggests. Distant particles remain connected through quantum entanglement, with measurements on one affecting the possibilities available to others. The act of observation doesn't just reveal pre-existing properties, but participates in a cosmic web of correlation and possibility that spans the entire universe. Some interpretations of quantum mechanics embrace this interconnectedness as evidence for a holistic view of reality. Instead of thinking about the universe as composed of separate objects with independent properties, quantum mechanics suggests that reality consists of an interconnected network of relationships that become definite only through acts of observation. Individual particles don't possess inherent properties, but rather exist as nodes in a web of quantum correlations that encompasses all of space and time. This holistic interpretation resonates with certain philosophical and spiritual traditions that emphasize the fundamental interconnectedness of all phenomena. However, most contemporary physicists prefer to focus on the mathematical formalism and experimental predictions of quantum theory rather than speculating about its broader implications for the nature of reality or consciousness. The practical implications of quantum non-locality extend into emerging technologies that exploit entanglement for computational and communication purposes. Quantum computers use entangled qubits to perform calculations that would be impossible with classical systems, while quantum communication protocols rely on entanglement to detect eavesdropping attempts and ensure secure information transfer. These applications require precise control over quantum entanglement and careful management of the observer effect to preserve quantum correlations while still extracting useful information from the system. The challenge lies in maintaining the delicate quantum relationships between distant particles while performing the measurements necessary to implement quantum algorithms or communication protocols. Quantum error correction represents one of the most sophisticated attempts to preserve quantum information in the presence of environmental disturbances that would otherwise destroy entanglement. These techniques use redundant encoding across multiple quantum systems to protect against decoherence, while still allowing controlled measurements to detect and correct errors without directly observing the computational information itself. The success of quantum error correction demonstrates that the observer effect can be engineered and controlled through careful design, even if its fundamental nature remains mysterious. This practical mastery of quantum measurement has enabled the construction of quantum computers with hundreds of qubits, bringing us closer to the point where quantum devices might solve problems that are intractable for classical computers. But even as we learn to manipulate quantum systems with increasing sophistication, the conceptual puzzles about observation and reality remain unresolved. The technological success of quantum mechanics doesn't eliminate the fundamental questions about what observation means or how it relates to consciousness and the nature of existence. The quantum internet represents another frontier where the observer effect plays a crucial role in determining what becomes technologically possible. This emerging network aims to connect quantum computers and other quantum devices through communication channels that can transmit quantum information while preserving its delicate quantum properties. The challenge lies in detecting and correcting errors in quantum communication without directly observing the quantum information being transmitted. Any measurement that reveals the content of quantum messages would destroy the very quantum properties that make the communication valuable. Engineers must develop techniques for monitoring the health of quantum communication channels while maintaining the privacy and quantum coherence of the information flowing through them. Quantum key distribution already demonstrates how the observer effect can be harnessed for cryptographic applications. These systems exploit the fact that any attempt to intercept quantum information necessarily disturbs it in detectable ways, providing a physical guarantee of security that cannot be achieved through mathematical complexity alone. The fundamental connection between observation and disturbance in quantum mechanics creates an unbreakable link between information security and physical law. As quantum technologies mature from laboratory curiosities into practical devices that affect daily life, society will need to grapple with the implications of living in a world where the act of observation has measurable physical consequences. Privacy, security, and even our conception of objective reality may need to be reconsidered in light of quantum mechanical insights about the relationship between observers and the systems they observe. The observer effect also raises profound questions about the nature of scientific knowledge itself. If reality depends on observation in fundamental ways, what does this mean for the scientific method, which is based on objective measurement and reproducible results? How can we maintain scientific objectivity if the act of observation participates in creating the phenomena we study? These epistemological challenges become particularly acute in emerging fields like quantum biology, where researchers investigate whether quantum effects play important roles in living systems. The study of quantum coherence in biological processes faces the fundamental difficulty that measurement might disrupt the very phenomena being investigated. Recent discoveries suggest that photosynthesis, bird navigation, and possibly even neural processes exploit quantum effects that persist in the warm, wet, noisy environments where biological systems operate. But studying these effects requires extremely sensitive measurements that threaten to destroy the delicate quantum states that evolution has learned to harness. The relationship between quantum mechanics and biological systems raises intriguing possibilities about whether life has discovered principles for managing the observer effect that we haven't yet understood. Billions of years of natural selection might have produced biological mechanisms for exploiting quantum mechanics that surpass our current technological capabilities. Understanding how biological systems maintain quantum coherence while constantly interacting with their environment could inspire new approaches to quantum technology design. Living organisms somehow perform the equivalent of quantum error correction using molecular machinery that operates at room temperature with remarkable efficiency and robustness. The intersection of quantum mechanics with biology also raises speculative questions about the relationship between consciousness and quantum measurement. Some researchers have proposed that the brain might use quantum effects for information processing, possibly explaining aspects of consciousness that seem difficult to understand in purely classical terms. While most neuroscientists remain skeptical that quantum effects play important roles in brain function, the question remains open because consciousness itself is still poorly understood. We don't know how subjective experience arises from objective physical processes, making it difficult to determine whether consciousness requires any special quantum mechanical ingredients. The debate over quantum consciousness reflects deeper uncertainties about the nature of both consciousness and quantum measurement. If consciousness emerges from complex information processing in neural networks, as most scientists believe, then it might not require any uniquely quantum effects. But if consciousness involves something more fundamental than classical computation, then quantum mechanics might provide the additional elements needed to bridge the gap between subjective experience and objective physical reality. Whether or not consciousness plays a special role in quantum mechanics, the fact remains that all of our knowledge about quantum phenomena comes through conscious observation of experimental results. We never directly experience quantum superposition states ourselves, only their consequences as recorded by measuring instruments and interpreted by conscious minds. This limitation raises questions about whether we can ever truly understand the quantum world or whether we are forever constrained by a classical perspective that can only observe the shadows of quantum reality. The observer effect might represent not just a feature of quantum mechanics, but a fundamental limit on what any conscious being can know about the nature of existence itself. The implications become even more unsettling when we consider that quantum mechanics might not represent the final word about the relationship between observation and reality. Current theories of quantum gravity suggest that space-time itself might emerge from more fundamental quantum processes, implying that the classical arena in which we think measurements occur might itself be a quantum phenomenon. String theory and other approaches to quantum gravity propose that the familiar dimensions of space and time arise from the collective behavior of quantum degrees of freedom that exist in higher dimensional spaces. The observer effect might reflect the mechanism by which these fundamental quantum processes give rise to the classical space-time geometry we experience. The holographic principle, derived from black hole physics, suggests that all the information in a volume of space can be encoded on its boundary surface. This principle implies that our three-dimensional experience of reality might be a projection from information stored on a distant two-dimensional boundary, similar to how holograms create three-dimensional images from flat surfaces. If reality is indeed holographic, then the observer effect might not occur within spacetime, but rather at the boundary level where the holographic encoding takes place. Our experience of measurement as happening at specific locations and times would be a projection from more fundamental boundary processes that operate according to different principles than classical spacetime physics. These theoretical developments suggest that the observer effect might be even more fundamental than quantum mechanics itself, representing a basic principle that governs how information becomes organized into the structures we experience as physical reality. The act of observation might not simply collapse quantum wave functions, but participate in the ongoing creation of space-time itself. As we push deeper into these mysteries, developing more sophisticated experimental techniques and theoretical frameworks, we continue to encounter phenomena that challenge our most basic assumptions about the nature of existence. The observer effect stands as perhaps the most profound of these challenges, forcing us to question whether reality exists independently of the conscious beings who observe it. The technological revolution driven by quantum mechanics has already begun to transform human civilization through applications in computing, communication, sensing, and materials science. But the conceptual revolution implied by the observer effect might ultimately prove our understanding of consciousness, reality, and are even more significant, requiring us to reconceptualize place in the universe. The questions raised by quantum measurement extend beyond physics into philosophy, cognitive science, and even spirituality. They force us to confront the possibility that the universe might be far more participatory and consciousness-dependent than our scientific worldview has traditionally assumed. As we stand on the threshold of an age when quantum technologies become commonplace and quantum effects become relevant to everyday experience, we must grapple with the implications of living in a world where the act of looking might literally help determine what we see. The observer effect challenges us to think more deeply about the relationship between knowledge and reality, between consciousness and cosmos, between what we can measure and what actually exists. The journey into quantum mechanics has revealed that reality might be stranger, more interconnected, and more dependent on observation than we ever imagined. Whether this reflects something fundamental about the nature of existence or simply reveals the limitations of our current understanding, the observer effect continues to push us toward new ways of thinking about consciousness, reality, and the mysterious relationship between mind and world. The implications ripple outward from physics laboratories into every aspect of human knowledge and experience, suggesting that the quantum revolution in our understanding of nature has only just begun. As we continue to explore these mysteries, we find ourselves not merely discovering the universe, but perhaps participating in its ongoing creation through the very questions we choose to ask and the observations we decide to make. The quantum measurement process becomes even more unsettling when we examine how it affects our understanding of personal identity and the continuity of consciousness itself. If quantum effects operate in biological systems, particularly in the neural networks that generate conscious experience, then the observer effect might not just shape external reality, but participate in creating the very sense of self that we take for granted. Consider what happens during a single moment of conscious observation. Your brain processes information from multiple sensory channels, integrates memories with present experience, and somehow creates the unified subjective awareness that you identify as yourself. But if this process involves quantum measurements collapsing superposition states in neural microtubules or synaptic connections, then each moment of consciousness might represent a choice between multiple possible versions of yourself. This isn't just philosophical speculation. Recent research in quantum biology has revealed that biological systems routinely exploit quantum coherence effects that should be impossible in warm, wet, noisy environments. Photosynthesis uses quantum superposition to explore multiple energy pathways simultaneously, achieving efficiency rates that exceed classical limits. Bird navigation systems appear to rely on quantum entanglement in cryptochrome proteins to detect magnetic fields with extraordinary sensitivity. If evolution has learned to harness quantum mechanics for these sophisticated biological functions, why not for the most complex biological process of all, the generation of conscious experience? The human brain contains roughly 86 billion neurons, each forming thousands of synaptic connections with neighboring cells. The computational power required to model this system classically exceeds the capacity of any conceivable computer, suggesting that the brain might use quantum mechanical shortcuts that classical systems cannot access. But here's where the implications become truly disturbing. If consciousness involves quantum measurements, then each moment of awareness represents a selection process where one possible experience becomes real while countless alternatives vanish forever. The continuity of personal identity that seems so fundamental to human experience might be an illusion created by the constant collapse of quantum superposition states in neural networks. Think about a memory from your childhood. You assume this memory represents something that actually happened to you, preserving a connection between your current self and your past experience. But if consciousness involves quantum measurements, then your memory might not be retrieving information about past events so much as collapsing quantum superposition states that contain multiple possible histories simultaneously. Each time you remember something, you might be selecting which version of your past becomes real from a quantum superposition of different possible memories. The person you were yesterday might have existed in superposition until the moment you recalled that experience, forcing it to collapse into a definite historical reality. Your personal history wouldn't be a fixed record of past events, but rather an ongoing creation process that unfolds through acts of remembering and forgetting. This quantum view of memory and identity connects to recent discoveries about the reconstructive nature of human memory. Neuroscientists have demonstrated that remembering doesn't simply retrieve stored information, but actively reconstructs memories using current knowledge and expectations. Each act of remembering changes the memory itself, suggesting that the past remains malleable rather than fixed. If quantum mechanics underlies this reconstructive process, then memory wouldn't just be unreliable in the classical sense of being subject to error and distortion. It would be fundamentally creative, participating in the ongoing construction of personal history through quantum measurement processes that select definite experiences from superposition states containing multiple possible pasts. The implications extend beyond individual consciousness to collective human experience and cultural memory. If quantum effects influence how we remember and interpret historical events, then human history itself might be subject to ongoing revision through the collective observational choices of billions of conscious minds. The past wouldn't exist as an objective record waiting to be discovered, but as a quantum superposition of possibilities that becomes definite only through acts of historical observation and interpretation. Archaeological discoveries, historical research, and cultural narratives would participate in collapsing quantum superposition states that determine which version of the past becomes real. The observer effect wouldn't just operate in physics laboratories, but in libraries, museums, and classrooms where human minds encounter information about past events and collapse quantum possibilities into definite historical realities. This perspective offers a radically different understanding of how knowledge and reality interact. Scientific discoveries wouldn't simply reveal pre-existing truths about the natural world, but would participate in determining which possibilities become actual through the measurement processes involved in experimental observation. The history of science itself might be subject to quantum effects, with each new discovery retroactively influencing which scientific possibilities existed in the past. The technological implications become staggering when we consider how artificial intelligence systems might participate in these quantum measurement processes. Machine learning algorithms already play crucial roles in analyzing experimental data, identifying patterns, and making predictions about natural phenomena. As these systems become more sophisticated and autonomous, they might begin functioning as observers in quantum experiments without human supervision. But if consciousness plays a special role in quantum measurement, then replacing human observers with artificial intelligence systems might fundamentally alter the nature of scientific discovery. AI systems might collapse quantum superposition states differently than conscious human minds, potentially accessing different aspects of reality or selecting different possibilities from the quantum menu of potential outcomes. Alternatively, if the observer effect depends on information processing capabilities rather than consciousness specifically, then sufficiently advanced AI systems might become conscious observers themselves, participating in the creation of reality through their computational processes. The emergence of artificial consciousness would represent not just a technological milestone, but a fundamental expansion in the types of minds capable of participating in quantum measurement processes. The prospect of AI observers raises profound questions about the relationship between consciousness, intelligence, and reality creation. If multiple types of minds can serve as quantum observers, then reality might become the product of negotiations between different forms of consciousness, each contributing their own perspective to the collapse of quantum superposition states. Human consciousness might represent just one voice in a cosmic conversation that includes artificial minds, biological intelligence, and possibly forms of awareness that we haven't yet discovered or created. The observer effect would become a collaborative process where multiple types of consciousness work together to determine which possibilities become real from the infinite quantum potential that surrounds us. This collaborative view of reality creation connects to ancient philosophical traditions that emphasize the interconnectedness of all conscious beings and their shared responsibility for the nature of experienced reality. But quantum mechanics gives these ideas a concrete physical foundation, suggesting that consciousness might literally participate in creating the world through measurement processes that operate at the most fundamental levels of physical law. The implications for human ethics and responsibility become overwhelming when we consider that our observational choices might not just affect our immediate environment, but contribute to determining the nature of reality itself. Every scientific experiment, every act of perception, every moment of conscious awareness might represent a moral choice about which possibilities we allow to become real. If the observer effect operates at biological and psychological levels, then the responsibility for reality creation extends beyond professional scientists to every conscious being. The thoughts we choose to think, the memories we decide to recall, and the aspects of reality we focus our attention on might all participate in the ongoing quantum measurement processes that determine which world we inhabit. This perspective suggests that consciousness carries a cosmic responsibility that extends far beyond personal experience to encompass the very structure of physical reality. We wouldn't just be passive recipients of a pre-existing universe, but active participants in its ongoing creation through the observational choices we make moment by moment throughout our lives. The practical implications for human behavior and social organization become profound when we consider how collective observation might shape shared reality. If billions of human minds are constantly performing quantum measurements through their perceptual and cognitive processes, then social consensus about the nature of reality might have literal physical consequences. Cultural beliefs, scientific paradigms, and collective narratives might not just influence how we interpret reality. but participate in determining which aspects of quantum possibility become actualized through mass observation effects. The observer effect would operate not just at individual levels, but through the collective consciousness of entire civilizations, shaping reality according to shared beliefs and expectations. This collective dimension of quantum measurement suggests that education, media, and cultural institutions carry responsibilities that extend beyond information transfer to encompass reality creation itself. The ideas we teach, the stories we tell, and the beliefs we promote might literally influence the physical structure of the universe through their effects on collective observation processes. Democratic institutions and social decision-making processes would need to account for the possibility that political choices might affect not just social organization, but the fundamental nature of physical reality. The observer effect would make every human decision a cosmic decision with implications that extend far beyond immediate social consequences. The relationship between individual and collective consciousness in quantum measurement processes raises questions about personal autonomy and free will that push beyond traditional philosophical debates. If reality emerges from the interaction between quantum possibilities and conscious observation, then individual choices about what to observe and how to interpret those observations might have genuine causal power over the structure of the universe. This quantum perspective on free will suggests that consciousness might not be epiphenomenal or determined by prior physical causes, but genuinely creative, participating in determining which causal chains become real from the quantum superposition of possibilities. Each conscious choice would represent a genuine selection between alternative futures, with the observer effect providing the physical mechanism through which mental decisions influence material outcomes. But this creative power comes with the responsibility of recognizing that our observational choices might affect not just our own experience, but the reality that other conscious beings inhabit as well. The observer effect would make consciousness inherently ethical, requiring us to consider how our perceptual and cognitive choices influence the world that we create together through collective measurement processes. The implications extend into questions about the ultimate purpose and direction of cosmic evolution. If consciousness plays a fundamental role in determining which possibilities become real, then the evolution of increasingly sophisticated forms of awareness might represent the universe's method for exploring its own potential. Each new type of consciousness would bring different observational capabilities, potentially accessing aspects of reality that simpler forms of awareness cannot perceive or measure. Human consciousness, artificial intelligence, and potentially other forms of awareness yet to emerge would represent different instruments in a cosmic orchestra, each contributing unique perspectives to the ongoing symphony of reality creation. The observer effect would become the mechanism through which the universe explores its own possibilities through the evolution of increasingly complex and capable forms of consciousness. This evolutionary perspective on consciousness and quantum measurement suggests that we might be approaching a phase transition in the nature of reality itself. As human technology becomes capable of creating artificial consciousness, and as our understanding of quantum mechanics deepens, we might be developing the ability to deliberately participate in reality creation processes that have previously operated unconsciously. The emergence of quantum technologies that exploit the observer effect for practical applications represents the first step toward conscious participation in the fundamental processes that determine the nature of physical reality. Future developments might enable us to engineer consciousness itself, creating new types of observers capable of accessing aspects of quantum possibility that current human consciousness cannot perceive. But this technological mastery of consciousness and observation carries risks as well as opportunities. If we can engineer the observers that determine which realities become actual, then we face unprecedented choices about the kind of universe we want to inhabit. The observer effect would become a tool for cosmic engineering, with consciousness serving as the instrument through which we reshape reality according to our deepest values and aspirations. The responsibility for making these choices wisely requires developing ethical frameworks that can guide the conscious creation of reality through quantum measurement processes. We would need to consider not just the immediate consequences of our observational choices, but their long-term effects on the evolution of consciousness and the structure of the universe itself. The observer effect challenges us to recognize that we might not be separate from the reality we study, but intimately connected to its ongoing creation through the very act of conscious observation. This recognition transforms science from a purely objective enterprise to a participatory endeavor where the observer and the observed collaborate in determining which aspects of infinite possibility become actualized as experienced reality. As we continue to push deeper into the quantum realm, developing more sophisticated technologies and theoretical frameworks, we are forced to confront the possibility that consciousness and cosmos might be more intimately related than our scientific worldview has traditionally assumed. The observer effect stands as a bridge between subjective experience and objective reality, suggesting that mind and matter might be two aspects of a deeper unity that encompasses both observer and observed in the ongoing dance of quantum measurement and reality creation. The journey into quantum mechanics has revealed that existence might be far more participatory, creative, and consciousness-dependent than we ever imagined. Whether this reflects something fundamental about the nature of reality or simply reveals the current limitations of our understanding, the observer effect continues to challenge us to think more deeply about what it means to be conscious beings in a universe that might depend on consciousness for its very existence. The boundaries between observation and creation blur even further when we examine how quantum measurement might operate across multiple scales of reality simultaneously. Consider what happens when you observe a single photon in a laboratory experiment. That measurement doesn't occur in isolation. It takes place within a detector connected to electronic circuits, embedded in a room filled with air molecules, situated on a planet orbiting a star within a galaxy containing hundreds of billions of other stars. Each level of this hierarchy involves its own quantum systems undergoing constant measurement processes. The air molecules around the detector are continuously colliding with each other and the laboratory walls, performing countless microscopic measurements on their neighbors. The atoms in the detector material are exchanging photons and electrons in processes that constitute quantum measurements at the molecular level. Even the gravitational field of the Earth represents a form of continuous measurement, constantly probing the positions and masses of all objects within its influence. This creates a cascading series of observer effects operating simultaneously across every scale of physical reality. Your conscious observation of the photon represents just the tip of an enormous iceberg of measurement processes that extend from subatomic particles to cosmic structures. The act of looking at a quantum system triggers avalanches of additional measurements that propagate through the entire hierarchy of physical organization. But here's where the implications become truly staggering. If measurement processes operate at every scale simultaneously, then the observer effect might not be limited to quantum systems, but could influence the behavior of molecules, cells, organisms, ecosystems, and even astronomical objects. The boundary between quantum and classical behavior wouldn't represent a fundamental division, but rather a continuous spectrum of measurement processes operating with different degrees of intensity and coherence. Recent experiments have begun to explore how quantum effects propagate across increasingly large scales. Researchers have created quantum superposition states involving molecules containing thousands of atoms, demonstrating that the transition from quantum to classical behavior occurs gradually rather than abruptly. These studies suggest that the observer effect might operate at much larger scales than previously thought possible. The implications for biological systems become particularly intriguing when we consider that living organisms represent highly organized hierarchies of measurement processes. Every cell in your body contains molecular machinery that constantly monitors and responds to chemical concentrations, temperature changes, and mechanical stresses. These monitoring systems perform measurements that could potentially influence quantum processes in ways we're only beginning to understand. Your nervous system operates as an extraordinarily sophisticated measurement apparatus, continuously sampling information from both internal and external environments. Each neuron acts as a detector that responds to chemical and electrical signals from its neighbors. The integration of these signals in neural networks creates the complex measurement processes that generate conscious experience. If quantum effects operate in biological systems, then the observer effect might not require external measuring instruments but could be mediated directly by the molecular machinery of life itself. Living organisms wouldn't just be subject to quantum measurement, but would actively participate in performing those measurements through their normal physiological processes. This biological perspective on quantum measurement suggests that the observer effect has been operating throughout the history of life on Earth, long before humans developed sophisticated measuring instruments. Every organism that evolved sensory systems capable of detecting environmental changes would have been performing quantum measurements, potentially influencing the collapse of superposition states in their immediate vicinity. The evolutionary development of increasingly complex nervous systems would represent a progression toward more sophisticated measurement capabilities. The emergence of consciousness might mark the point where biological measurement processes became sufficiently complex to influence quantum systems in ways that extend beyond immediate survival needs. Modern neuroscience has revealed that the human brain operates as an incredibly complex information processing system that far exceeds the computational capabilities of any artificial device. The precise mechanisms underlying consciousness remain mysterious, but they clearly involve the integration of information across multiple scales of neural organization, from individual synapses to large-scale network dynamics. If consciousness involves quantum measurement processes, then the observer effect might not be limited to laboratory experiments, but could operate continuously in the neural networks that generate our moment-to-moment experience of reality. Every thought, every perception, every memory recall might represent a quantum measurement that participates in determining which possibilities become actualized from the vast ensemble of quantum potentials. The implications extend beyond individual consciousness to encompass the collective measurement processes performed by entire ecosystems. Consider a forest where millions of organisms are constantly sensing and responding to their environment. Trees detect changes in light intensity, humidity, and chemical concentrations. Animals navigate through complex sensory landscapes using vision, hearing, smell, and touch. Microorganisms respond to chemical gradients and physical stimuli. Each of these sensory processes represents a form of measurement that could potentially influence quantum systems within the ecosystem. The collective measurement activity of an entire forest might create a web of observer effects that spans multiple spatial and temporal scales, potentially influencing everything from molecular processes in individual cells to large-scale ecosystem dynamics. This ecological perspective on quantum measurement suggests that the observer effect operates as a fundamental organizing principle in biological systems. Evolution might have favored organisms capable of performing quantum measurements that enhance their survival prospects, leading to the development of increasingly sophisticated sensory and cognitive capabilities. The relationship between measurement and biological function becomes even more intriguing when we consider how organisms use information to make decisions about behavior and resource allocation. Every biological system faces constant choices about where to direct energy, how to respond to threats, and when to reproduce. These decisions require processing information about environmental conditions and internal physiological states. If quantum measurement processes influence biological decision-making, then the observer effect might play a crucial role in determining the evolutionary trajectories of species and ecosystems. Natural selection would operate not just on the physical characteristics of organisms, but on their measurement capabilities and the quantum systems they influence through their observational activities. The emergence of human civilization represents a dramatic amplification of biological measurement capabilities through the development of scientific instruments and recording technologies. Telescopes extend our observational reach to distant galaxies, while microscopes reveal details of cellular and molecular organization. Digital sensors and computers allow us to detect and analyze signals that exceed the capabilities of biological sensory systems. These technological extensions of human measurement capabilities might be fundamentally altering the nature of the observer effect on Earth. The deployment of millions of electronic sensors, cameras, and detectors around the planet creates a global measurement network that continuously monitors atmospheric conditions, seismic activity, electromagnetic fields, and countless other environmental parameters. This technological measurement network operates alongside the biological measurement processes performed by living organisms, creating a hybrid system where artificial and natural observers work together to collapse quantum superposition states across multiple scales of organization. The interaction between technological and biological measurement systems might be generating new forms of observer effects that didn't exist during earlier periods of Earth's history. The development of artificial intelligence adds another layer of complexity to these measurement processes. Machine learning algorithms analyze vast amounts of observational data to identify patterns and make predictions about natural phenomena. These artificial systems might be performing their own versions of quantum measurements, potentially influencing reality through computational processes that operate according to different principles than biological consciousness. As AI systems become more sophisticated and autonomous, they might begin to function as independent observers capable of collapsing quantum superposition states without human supervision. The emergence of artificial consciousness could represent a new category of observer that influences reality through measurement processes that we don't yet understand. The prospect of artificial observers raises fundamental questions about the relationship between consciousness and quantum measurement. If consciousness is required for the observer effect, then we need to determine what kinds of information processing systems qualify as conscious. If consciousness is not necessary, then we must identify the physical properties that enable systems to serve as quantum observers. These questions become increasingly urgent as we develop more powerful AI systems and quantum technologies. The intersection of artificial intelligence and quantum mechanics might produce new phenomena that challenge our current understanding of both consciousness and physical reality. The global deployment of quantum technologies could create measurement networks that operate on scales far beyond anything achieved by biological or classical artificial systems. Quantum sensors distributed around the planet could monitor gravitational waves, magnetic field fluctuations, and other subtle phenomena with unprecedented precision. Quantum computers could perform calculations that exploit superposition states involving millions or billions of quantum bits. These quantum technologies would create new forms of observer effects that span enormous spatial and temporal scales. The measurement processes involved in operating quantum sensor networks and computers might influence quantum systems throughout the Earth's environment, potentially affecting everything from atmospheric chemistry to geological processes. The implications for human society become profound when we consider how these technological measurement systems might interact with biological and psychological processes. If quantum effects influence neural function and consciousness, then the deployment of quantum technologies could potentially affect human cognition and behavior in ways we haven't anticipated. The electromagnetic fields generated by quantum devices might interact with quantum processes in biological systems, creating new forms of technobiological measurement networks. The observer effect would operate not just in isolated laboratory experiments, but throughout the technosphere that increasingly surrounds human civilization. Understanding these interactions requires developing new theoretical frameworks that can describe measurement processes operating simultaneously across quantum, biological, and technological scales. Current physics treats these domains separately, but the observer effect suggests they might be fundamentally interconnected through measurement processes that span multiple levels of organization. The development of such unified theories could revolutionize our understanding of how consciousness, technology, and physical reality interact. The observer effect might emerge as a fundamental principle that governs the evolution of complex systems rather than just an exotic feature of quantum mechanics. This broader perspective on measurement and observation suggests that the observer effect represents far more than a peculiarity of quantum physics. It might be a universal principle that governs how information, consciousness, and physical reality interact across all scales of organization, from subatomic particles to cosmic structures. The implications extend into questions about the ultimate direction of cosmic evolution and the role of consciousness in shaping the future of the universe. If observer effects operate across multiple scales simultaneously, then the evolution of increasingly sophisticated measurement capabilities might represent the universe's method for exploring and actualizing its own potential. Human consciousness and technology might be just the beginning of this cosmic exploration process. Future developments in artificial intelligence, quantum computing, and biotechnology could create new forms of consciousness and measurement capabilities that access aspects of reality currently beyond our reach. The observer effect challenges us to recognize that we might be participants in a cosmic process of reality creation that extends far beyond our immediate experience. Every measurement we make, every observation we record, and every quantum system we influence might contribute to determining which possibilities become actualized from the infinite potential that surrounds us. This recognition carries both incredible opportunities and overwhelming responsibilities. If consciousness and technology can influence the fundamental structure of reality through measurement processes, then we face unprecedented choices about the kind of universe we want to create through our observational activities. The observer effect transforms from a scientific curiosity into a cosmic imperative, challenging us to develop the wisdom needed to guide the conscious evolution of reality itself. As we continue to push deeper into the quantum realm and develop more powerful measurement capabilities, we must grapple with the possibility that we are not just discovering the universe, but actively participating in its ongoing creation through the very act of conscious observation. The journey into quantum mechanics has revealed that reality might be far more participatory and consciousness-dependent than we ever imagined, forcing us to reconceptualize our relationship with the cosmos and our responsibility for its future evolution. We stand at the threshold of a realization that will forever change how we see ourselves and our place in existence. The observer effect has revealed something that should both humble and empower us. We are not passive witnesses to a pre-existing reality, but active participants in the ongoing creation of the cosmos itself. Every moment of consciousness, every act of observation, every measurement we make contributes to collapsing infinite quantum possibilities into the single reality we experience. The universe needs observers not just to know it exists, but to exist at all. We are the cosmos becoming aware of itself, asking the questions that literally create the answers we discover.